Okay, so welcome everyone to the last episode of season 7 of the Isogeny Club. But we have a great talk saved for the last talk. It's Alessandro Sferlazza from the Technical University of Munich, who's gonna talk to us about computing the trace of endomorphisms. So please, Alessandro, take it away.
Thank you. Hi, everyone. Thanks for having me here for the lovely introduction. So today's project focuses on the computation of traces of elliptical endomorphisms using the theory of p-adic lifting. It's a recent joint project with Lorenz, Panny, and Damien. They're both in the audience in case you have very hard questions. And so, yeah, let's start. As usual, and in order to fix some notations, today's protagonist will be an elliptic curve, who could have guessed, over a finite field, let's say fq, where q is a prime power, and we'll work throughout the talk with a fixed endomorphism of this elliptic curve defined over the same base field. So whenever we talk about endomorphism rings, usually we know that abstractly such a ring is isomorphic to either an order in a quaternion algebra or the ring of integers or some suborder in a quadratic imaginary ring of a Q. But the thing is, can we make this correspondence explicit? Like given an endomorphism as an algorithmic isogeny, can we say which quaternion it is? In order to do that, we can observe that endomorphisms are quadratic integers, the roots of monic polynomials with integer coefficients, where the degree zero term is the degree of the isogeny itself. So it's usually built in the way we represent an endomorphism algorithmically on our computer. And there's this other degree 1 term, the trace, that together with the degree gives us a complete description of the endomorphism as a quadratic integer. As an overview, there are the algorithms to compute traces have been out of fulcrum for 10 years, pretty much. So in 2018, we got this algorithm by Bank, Camacho Navarro, Entrega, Morrison Park, that adapted Schoof-style algorithm and created a polynomial time algorithm to compute traces of both ordinary and supersingular curves. Then this year, Morrison, Panny, Sotakova, Wills observed some speed ups in supersingular case. And in this talk, we try to lower the complexity even more to a cubic algorithm in the size of the inputs that is supposed to be general and apply to both ordinary and supersingular curves. In order to devise a trace computation algorithm, the starting point is always point counting, because that's a classical problem in number theory. Given an elliptic over a finite field, we want to know how many rational points there are in this over this finite field. And the thing is, if we consider the Frobenius endomorphism, like the Q powering of coordinates, where Q is the size of the base field, then this endomorphism is also a quadratic integer, since it's an endomorphism. It has degree Q, where Q is, again, this size of the base field. And the trace of Frobenius is directly connected with a number of rational points by a very simple formula. So in particular, the problem of point counting and problem of computing the trace for this endomorphism are equivalent. So thanks to this observation, the state-of-the-art algorithm for trace computation used the first algorithm for point counting that was devised by Schoof, proposed in the 85, and optimized by Zatkin, and then further optimized in the past 2 decades. That basically tries to compute the trace of this Frobenius endomorphism modulo many small primes and combine to get a trace as an integer. So the current trace computation algorithms are a variant of these, but there's actually an alternative approach to point counting proposed by Satoh in 2000 and then further optimized in, in the following years. That uses a different theory, the one of p-adic liftings and the action of differentials, or the action of endomorphisms on locally invariant differentials on a curve. And this is our starting point. This is the approach we're trying to generalize to general endomorphisms for a trace computation. So let's see in detail what these ingredients are about. The first ingredient that we consider is this of differential scaling factors. What is it about? Basically, if we look at an elliptic curve locally, well, it's a smooth curve. So around every point, the curve can be like locally approximated by the line. It looks like the base field because it's a line. And since it's also an algebraic group, all these tangent spaces, all these lines must be compatible with one another. There must be a correspondence that when we translate by a point, so we shift points around, then this line also shifts. So there's a way to describe all these lines at once. That is a translation invariant differential. It has a simple expression in coordinates if we represent E as a as a short Weierstrass curve. But not only translations interact with these differentials. Actually, every isogeny interacts with tangent spaces in the sense that this line around P can be stretched, can be shrinked via the action of an isogeny through a scaling factor that acts on these differentials. And that is actually quite explicit once we look at the at the rational functions that define the isogeny itself. So if we look at the isogeny written in coordinates, we consider the rational function for the x, its derivative, the y coordinate, then C is written there, which means if phi is an isogeny of very high degree, so computing this f and f prime is quite hard. But if phi is a small degree isogeny, then writing these coordinates explicitly is kind of is easy. So we can retrieve a scaling factor from such an isogeny. And then by multiplicativity of scaling factors, whenever we have a chain of small isogenies, which is the way we usually represent them on a computer, then the scaling factor of the composition is actually just the product of the single scaling factors of the individual steps. So whenever we've got a chain, we've got a computational way to retrieve a scaling factor. Now, how do we use them? The thing is, we don't just have a mapping from an endomorphism to its corresponding scaling factor, but this is actually a ring home from the endomorphism to the field definition of the curve. And in particular, this homomorphism preserves algebraic relations. So if phi is a root of its characteristic polynomial, then its scaling factor will be a root of the same characteristic polynomial, which means if instead of computing the trace of the endomorphism, we can compute the trace, that is the degree one term in the of this scaling factor. And so this integer t will be the same. And since c is now a number, this scaling factor c phi, then the trace can actually just be computed as one root of this polynomial, this c, times the other root, that is d divided by c. Now, one of the key insights here is that, well, the trace must be an integer, so this t must be an integer. But, so an integer multiple of 1, but when these numbers live in a finite field of characteristic p, then we can only get the integers as an integer modulo p. So our strategy will be to lift the curve from a finite field to something of characteristic 0, so that now we get an endomorphism that lifts the one we had before, but lives in characteristic 0. So now the trace will be the same, but will be an actual integer, because in characteristic 0, the integers embed in our ring. So in order to compute a trace, we need these two ingredients: how to compute a scaling factor of a given endomorphism, and how to lift from a finite field to something that lies above. So let's see how. Let's dive into this problem of lifting. Yeah. The instrument, the tool that we're gonna use is the ring of the p-adics, that we can define simple way as a formal, like the ring of formal power series in P, where the coefficients are integers between 0 and p-1, so basically representatives for the finite field Fp. And if we set P to be 0, that is, we're left with just the degree 0 term, then we got a projection from this ring of the characteristic 0 to a corresponding finite field. And with this idea of having a series in P with coefficients in this finite field, we can actually generalize that to lift any finite field extension. Again, with the same idea, constructing series, like power series in P, where now the coefficients are representatives for this finite field. So basically we can get something characteristic 0 that lies above any finite field of our choice. Of course, when you represent such numbers here, such power series, we cannot represent the whole series because it's infinitely many things. So we truncate elements to finite precision. Let's say we store the first k terms, and then the rest is implicitly collected as big O of p to the k, like multiples of p to the k. But in particular, when we just keep the degree 0 term, and as we consider the finite field element line below, then we can see finite field elements as just p-adics of precision 1, where everything that is multiplied by p is sort of ignored. How do we use these p-adics? The idea is that we want to be able to lift an object that lies in a finite field to something above. So a lift must reduce back, must be an actual lift, so must reduce back to the things we had when we consider it modulo p. And whenever A satisfies a property, we want to preserve this same algebraic property on the lift. Concretely, we can do that when A is a root of a polynomial. That is what Hensel's lemma tells us. Basically, yeah, and we've got a polynomial over this characteristic 0, so this p-adic ring, ZQ, that is a simple root, that is the derivative modulo p is non-zero, and A is a root modulo p. Then this object, this root of a polynomial, can be lifted to something that indeed reduces back to what we wanted and is still a root. More generally, apart from roots of polynomials, we can consider many polynomial equations. So we can lift roots of systems of polynomial equations by just increasing the dimension of this polynomial function. It becomes a polynomial map. And instead of requiring the derivative to be non-zero, we require surjective Jacobian matrix, a surjective differential at a given point. And even more generally, we're not even restricted to polynomials, but anything that admits a derivative, so any differentiable function, or let's say the fractional field of this ring, is actually accepted, and to such functions, Hensel's lemma applies. Like p-adic rings, p-adic fields are equipped with p-adic topology, which is not the same as the Euclidean one on R, but also allows for definition of convergence, limits, derivatives, so we can actually perform calculus on such fields. So in particular, we can use Taylor's expansion, we can use derivatives. So yeah, more concrete, to go more concretely, so Hensel tells us that whenever we have a simple root modulo p, we can lift it. And how can we do that in practice on a computer? The idea is we've got something modulo p, and then using Newton's iterations, step by step, we can double the complexity every time. So we can bring something modulo p to something modulo p squared, then modulo p to the fourth, and then double as much as we want in logarithmic time. And to do that concretely, let's say we've got such an object, a root of a polynomial modulo p, and we want to transform it to an element modulo fp squared. So we take the residue modulo p and we add some multiple of p yet to be determined. How do we decide which multiple is the correct one? Well, we must impose that the lifted element, so this a plus dp, is also a root of the same polynomial. And since that is a polynomial, we can expand it using Taylor's expansion. And that, as soon as we ignore powers of p squared, because we're considering everything modulo p squared, we basically get a linear equation in this t that we want to retrieve, where the coefficients depend on the evaluation of this polynomial function on a and its derivative modulo p squared. So now from p, we lift to precision, so to modulo p squared, and then we can keep doubling. So whenever we've got p to the fourth, we get to p to the eighth, and so on. And to be even more concrete, let's take an example. Given an elliptic curve, we've got point of order 2. So basically, an x-coordinate whose corresponding y-coordinate is 0. And we want to lift that. So let's say we decide a lift of the curve where the lift has to live by just lifting the coefficients of the curve one by one to something in higher precision, let's say modulo p squared. And now being of order 2 means, again, that the x-coordinate is a root of the defining cubic. So lifting the point amounts to lifting its x-coordinate as a root of a polynomial. So we want to lift the root of this cubic, and how we do? We just set up this linear equation, and t will become a ratio of something depending on like the cubic divided by p. We know that this cubic is divisible by, like, is 0 modulo p by assumption. And the denominator has the derivative, which in this case is simple to write. It's just the derivative of a cubic. And also shows why we want the derivative to be non-zero, because it appears here at the denominator. But what's the thing? So we can do that with small polynomials like this. But what if we want to lift a polynomial that is like a root of a polynomial that is much bigger? Like, for example, what if instead of a 2 torsion point, we want to lift point of order much larger, let's say to the like a big power of 2. And in that case, instead of just the defining cubic, we have to deal with a division polynomial of high order. And this thing can be quite large to store on a computer in order to compute the derivative easily. So yeah, we've got some kind of a problem, but let's see how we can overcome that. So I'm restating the problem here. We've got a root of a polynomial. We want to lift it to double precision. And in order to do that, we need a linear equation where the coefficient depends on the evaluation of a polynomial function and its derivative. And a key insight here is that even if f can't be written explicitly, a black box way to evaluate it is sufficient, because then we just evaluate it in higher precision to, let's say, a modulo p to the 2k. So a in double precision, we evaluate it and we get f of a in double precision, and then a closed lift a plus a multiple of p, like of p to the k. And by Taylor's expansion here, we get an extra factor that depends pretty much explicitly on the derivative that we're after. The idea is, again, first order Taylor's expansion, because we can ignore stuff that is second order. We ignore 2 to the k, like two times even powers of p. And basically every polynomial function that we're considering can be approximated as a line. So evaluating in 2 convenient points that are close to each other in p-adic topology makes the function look affine linear. So yeah, given 2 points, we can compute the slope, that is the derivative of a function. And for that, we just need 2 black box evaluations in high precision. So the take home here is, even if f is implicit, we don't ever write it down explicitly. We just got an algorithm to compute it. We can still find its derivative at any point that we like. And now let's specify to our favorite field of interest. Instead of just roots of polynomials, can we lift some more complicated objects? The theory says that, I mean, an old theory that dates back to Serre and Tate, and then Messing wrote the proofs, Gross added some bit of theory. Says that when we have an elliptic curve or a finite field, and we consider a non-trivial, let's say, separable endomorphism, then this endomorphism can be lifted like together with a curve uniquely to the p-adics in such a way that the endomorphism ring of the lift is actually pretty much described by this lifted endomorphism. So the known case that has been studied already regarding like Satoh's algorithm and these point counting algorithms, it is classical in algebraic geometry, is the theory of canonical lifts. That is, when we've got an ordinary elliptic curve, then we can lift not the Frobenius because that's inseparable, but let's say the dual, the Verschiebung, and lifting that gives us a canonical lift whose endomorphism ring is exactly the same as the one below. We've got a thing below and a thing above. In general, of course, the endomorphism ring of the elliptic curve below will be larger. For example, on a supersingular curve, you get something that is a lattice and a quaternion algebra, so rank 4 instead of rank 2. But we always have at least an injection from the endomorphism ring of the thing above to the endomorphism ring of the thing below, of the elliptic curve below. And in particular, such an injection is a ring homomorphism again. So it preserves characteristic polynomials, it preserves traces. So basically, yeah, lifting such a polynomial, such an endomorphism to characteristic 0 to the p-adics gives us something with the same trace. That is what we wanted for our trace computation algorithm. In order to perform such a lifting algorithmically, let's see more concretely how we can do that. Lifting a curve basically amounts to just taking the coefficients one by one and lifting them to high precision. Whereas lifting an algorithm really depends on how we say that on a computer. So what are the possibilities to represent an algorithm on a computer? Let's review them quite fast. Let's say our algorithm is our isogeny. We've got a separable isogeny between 2 elliptic curves. In In case it has smooth degree, which is the most common case in isogeny-based crypto, then the isogeny factors as a long chain of small steps of small prime degree. And each one of the steps can be represented by a kernel point. That is, given a kernel point using Vélu's formulas or faster algorithms, like asymptotically faster algorithms like square root Vélu, we get an algorithm to compute all these intermediate codomains, including the final one, so the actual codomain of the curve, and an evaluation algorithm that taken any point in the domain gives us the output of the isogeny in the codomain. So those two properties together, say that can be condensed in the definition that this string E and all these kernel points of the steps are an efficient representation of the isogeny, that is, give us the codomain and an evaluation algorithm. And of course, apart from Vélu, there are other possibilities. For example, instead of saving a kernel point for every step, we can save the J invariant of the intermediate curves. We can use radical isogenies and just choose a choice of an Lth root at each step, direction in the isogeny graph. Or there are big fans of that in the audience, I guess. We can change approach and represent isogenies by their HD representation. We'll cover that in a bit. But so let's go in detail over the lifting. So let's see how to lift a single isogeny step. Let's say we've got a phi from E0 to another elliptic curve E1 of small, let's say, prime degree. And so first thing we do is choose pretty much arbitrarily the lift, like a lift of the domain. And then if the isogeny step is represented by a point, then we want to lift this point. And now let's see concretely how to lift a point. Like a point is given by two coordinates, x and y, and they must satisfy some constraints. Like, for example, we need to make sure that the lifted point p tilde is a point over the L in the lifted curve. And that amounts to the x coordinate being a root of the division polynomial. So we can lift that, a root of a polynomial. We know how to do that. Actually, we can observe here that the division polynomial also depends polynomially on the coefficients of the curve. So instead of just lifting x using a Newton's iteration, we can compute partial derivatives. That is the dependency of this function locally on all the variables. And that gives us a linear dependency relation between x and the x coordinate of the point and the coefficients of the curve that ensure when we lift, we know how to set them so that the lift is still a point of order L. And similarly, we can make sure that now the point xy lifted also lies in the curve. That is, x and y must satisfy the defining polynomial of the curve. So in particular, doing the same trick, we can find a linear dependency relation between the coefficients of the curve and the coordinates of the point we're considering. So to lift an isogeny step is basically just lifting some variables, x, y, a, b, as roots of a polynomial system of equations. There are, of course, alternatives, like if you've got J invariants, there's another, like a different polynomial, a different algebraic set of constraints, like an algorithm by Bostan, Morin, Salvi, Schost in 2008, computes a codomain in a canonical way, let's say, of the given J invariant and an isogeny that is normalized. And the thing to note here is that the codomain, the coefficients of the codomain are algebraically dependent on the input. They're a rational function. They're expressible as a rational function of the J invariant and the domain curve. With a disclaimer, when one of the J invariants is 0, 17, 28, of course, we have problems. For example, this isogeny here can be non-unique. The mapping that goes from the J invariant to the curve is also non-smooth around this point, so that gives us problems, but there are workarounds for that. So now that we know how to lift an isogeny step as a root of a polynomial system of equations, we're ready to lift a whole chain. Let's say we've got a chain of isogenies where every isogeny is, for example, represented by its kernel point. Then we first lift the initial curve, and then we lift a step. We just seen how to do that. So once we've lifted a step, that is lifted its kernel point, we can define the intermediate codomain above. So this E1 tilde to be the result, the codomain of this isogeny step. This E1 tilde will be an actual lift of E1. And then step by step, we just go forward. We lift one, we lift the other until we lift all of them. And yeah, and that's how we lift a chain of isogenies, just by lifting all the steps, all the parts one by one. Of course, this is not specific to Vélu's formulas. We can use squared Vélu, that is same representation, different algorithms. We can use radical isogenies. We can use all sorts of chains that we like here. Okay, there are some more details to cover. That is, what happens when we have an isomorphism between two curves over a finite field? Can we lift that? We know that whenever we've got two curves, so let's say in Weierstrass form, short Weierstrass, then the coefficients of one another are rescaling by powers of a certain isomorphism factor, let's say some u. And this u actually up to sign also determines an explicit isomorphism between the two curves. That is, even at the level of coordinates, just a rescaling by a power of 2, by a power of this u. So the thing is, lifting an isomorphism amounts to lifting this number here, this u, an isomorphism factor. And also, I mentioned at the beginning how to get scaling factors of stuff of isogenies of small degree, and of course, degree 1 is quite small. In particular, in this, so in the case of Weierstrass isomorphisms, the differential scaling factor can be just read off because it's the inverse of this coefficients u. Why do we ever need that? Because now consider, let's go to the juicy bit. Consider the situation where we've got an endomorphism and we want the lift to also be an endomorphism, like a proper thing that goes from a curve to the same curve. If, let's say, our endomorphism is represented algorithmically as a chain, and using the recipe that we've got so far, we can lift the chain and we'll get an isogeny over the p-adics that goes from a curve, a lifted curve E1 tilde to a lifted curve E2 tilde. And we know that both curves are lifts of the same E, but these two don't necessarily, they don't need to be the same. So we need to somehow enforce an extra constraint when we lift that. That is, we want to impose another algebraic, like sort of rational polynomial constraint on our set of polynomial constraints that the input coordinates are subject to. Namely, this extra constraint we want to impose is just that the domain is the same as a codomain. So this E1 tilde must be the same as E2 tilde in our lift. This is again something algebraic, so can be achieved again using Hensel. Again, the same strategy. So for example, to be more explicit, let's say we've got an endomorphism that is represented as a value chain. So we've got the usual data, domain, and all the kernel points of the steps. And then a final isomorphism, so that whatever we've got from the chain, it'll be something isomorphic to the domain, and then we consider the isomorphism through this isomorphism factor U explicitly. That gives us a recipe to compute an isogeny that goes actually from a given curve to exactly the same curve. So to lift that, well, we first lift the chain as we know how to do, but imposing the extra constraint that the initial curve is the same as the final one. And then once we know that E0 tilde and En tilde are isomorphic, we also lift the isomorphism by just lifting the factor. So that we're sure that the coordinates after the whole cycle here are exactly the same, even over the p-adics, even in a lift. So yeah, what we've seen so far is we can lift a single step, we can lift chains, and we can lift endomorphism with the constraint that the domain and the codomain coincide exactly, not just up to isomorphism. Yeah, that's a way to lift endomorphism in the case of chains. Can we do that higher dimensions now? I know they're like big fans. So so let's say we've got a separable isogeny of odd degree, so some 5 from 0 to a1. And now very short summary of the last 3 years of isogeny-based crypto will be that we can embed this one-dimensional isogeny into something two-dimensional. That is, this one-dimensional isogeny fits in a commutative square. And now if you take the diagonals of the square, 0 times E3, we can construct, sometimes with conditions, a two-dimensional isogeny to another product, namely the other diagonal of the square, so that if we take a point of E0, we embed it in the product, we perform the two-dimensional isogeny, and then we take just one component of this two-dimensional thing. Then we've got exactly the isogeny we wanted. So basically taking the domain and a basis of the kernel of such an isogeny gives us an efficient representation. Something that efficiently allows us to compute the codomain and evaluate the isogeny on any point. Again, in 2 dimensions, this thing will be smooth. So basically it'll be a chain. The idea of lifting is the same, but the thing is we can lift it. So in order to do that, let's see the steps. We need to lift the kernel points to be points that lie on the actual lifted domain and have the correct order. And there's one complicated thing on in dimension 2 that didn't appear in dimension 1. That is, normally in such a 2-2 isogeny chain in dimension 2, we start like from a product of elliptic curves. We go through Jacobian, 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 and then we split at the end again. Now, when we lift that, well, we first lift the domain to be, again, a product of elliptic curves, and then we perform the steps because we lifted P and Q. So we go through Jacobian, Jacobian, Jacobian. But then, when we want to split again, it is not automatic that the final thing will be a product instead of a Jacobian. So that's another constraint we need to impose. Like we need to make explicitly sure that the final thing splits again, because then we can recognize some lift of E1. And yeah, what else do we need to lift? Well, if E0 and E1 are the same curve, that is, if we're lifting an endomorphism, we want to also make sure that these two things in the end are at least isomorphic. So even for a two-dimensional isogeny, we've got a bunch of algebraic constraints that we can apply Hensel's lemma to in order to get a lift over the p-adics. And of course, don't worry, this thing doesn't just apply to 2 dimensions, but 4 dimension, 8 dimensional isogenies also follow the same strategy to be lifted. So take the one you like the most, you can lift it. And that's of course not a coincidence, because there's not much special about a chain or a HD representation. The thing is, given most of the isogeny representations you can think of, like using the defining polynomials, describing it as a sum of morphisms, you can still lift the representation as long as I've got some requirements. That is, the computation is a regular function, like it's a rational function, for example. Like the output of the isogeny algorithm should depend in a like kind of smooth way on the input. For example, this applies to all the algebraic computations that only use sums, products, divisions. So that implicitly could be described as a rational function, even with integer coefficients on the input. So whenever we've got such a circuit, we can lift it. And for example, Vélu's formulas are such a circuit, or square root Vélu also applies. With a caveat, we should make sure that the input we've got is not a critical point on this implicit rational function described by our algebraic computation. That is, we need to make sure that all the derivatives involved of the things we want to lift are non-zero modulo p. So for example, we usually need isogenies to be separable, because for inseparable isogenies, we get, for example, the x coordinate of the isogeny that is a p power. So whenever we derive that, we get p times something, which is 0 modulo p. And that's why we require isogenies to be separable. But apart from isogenies or polynomial constraints or rational functions, we can actually do much more. Like we're not that restricted. We can do, for example, we can, I don't know, lift some consistent choice of a square root mapping from x to square root that is compatible with the p-adic topology, as long as we're away from the problematic points like 0. Or given an isogeny, we can lift the representation of its dual, of some inverse maps, of some special point with the properties we want. And as long as they're algebraic or regular, we're happy. So I don't know, I find it a cute idea. There was a problem that I left unsolved from the beginning. That is, in general, how can we compute a scaling factor? We've seen that for chains, for compositions of stuff of small degree and isomorphism, which are also kind of small degree because they're isogenies of degree 1, we know we can combine scaling factors of the single steps. And in particular, Vélu's formulas give us isogenies that are even normalized. That is, the scaling factor is always 1. No need to worry about that. And the scaling factors of isomorphisms can be read off the isomorphism itself. So whenever we've got a composition of those things, we know how to retrieve a scaling factor. But in general, how to do that? The idea here is that given an algorithm to evaluate phi, then whenever we've got p with its coordinates, the isogeny gives us the coordinates of the output, let's say some x and some y. And actually, these x and y can be written explicitly, like more or less explicitly. Because if we call f the rational function that expresses the dependency of the x coordinate, then the y coordinate will depend on the y coordinate of the original point, the derivative of this function, and the scaling factor. Through Hensel, we saw that even if f is not explicit, we've still got a black box evaluation algorithm. So with two evaluations of this algorithm, we can get both the function itself and its derivative. Again, by the trick of approximating the function as a line, with a line. And from this information, finding the scaling factor of a general isogeny, whatever the efficient representation is. So even for HT isogenies, not just for chains. Then in this case, C will be just recoverable through a division over the finite field we're working in, or the, yeah. So that is quite convenient. No need for the isogeny to be just a scaling factor, a chain. This can actually be retrieved all the way. So in order to wrap up, what do we have? We've got, we started with an elliptic curve and an endomorphism over a given finite field, and we wanted to compute the trace. So the first observation is the endomorphism phi is an imaginary quadratic element. So it's like the discriminant of its characteristic polynomial is negative, which gives us a bound on the trace, namely in absolute value that's smaller than the square root of 4 times the degree. And that gives us a sort of goal to which p-adic precision we want to lift, we want to arrive. Namely, if we choose a small k such that p to the k is larger than twice the bound for the trace, then basically p to the k will be larger than the possible, like the number of values that the trace can assume. I mean, it's an integer in a bounded interval, and p to the k is larger than the the number of possible values. So if we get an elliptic curve and an endomorphism, and we lift it to such a precision, we get something that is defined over the p-adic ring with precision k, so modulo p up to multiples of p to the k. And now in this ring, we can compute the scaling factor. We saw the trick, so we can do that. Quite convenient. And once we can get a scaling factor that also lives in the same ring p-adic modulo p to the k. And that's basically almost the solution, because then given this number plus d divided by this number, we get the trace modulo p to the k. We can like imagine its representative to be centered around 0. But since we know that the trace as an integer should coincide with this t modulo p and it's bounded, then the like mod p to the k value that we got is actually exactly the integer value of the trace. So through this bound, lifting, and computing a scaling factor, we got the trace. How complex is that? The hardest, let's say the slowest step of all this computation is hence lifting to the biggest precision. That's the bottleneck. And like as we saw, lifting amounts to computing at least 2 times, but actually depending on the representation can be up to like 3, 6 at the high precision. So yeah, let's say the main part of the cost is re-evaluating the isogeny a constant number of times. So in the end, the complexity, but in the ring ZQ modulo p to the k. So the complexity of this whole algorithm, that is the complexity of this heavy lifting, is the cost of the isogeny itself. So how many, in the case of an isogeny chain, it will be number of steps plus cost times cost of a step. And we need to take into account the cost of arithmetic in this large, let's say, high precision ring, which is basically quadratic in the precision and in the logarithm of p as well. That's implicit everywhere. So considering that given the bound k also grows logarithmically with a degree, same as n, then evaluating the isogeny is linear in the number of steps. This arithmetic is quadratic, so the final cost is like quasi-quadratic. So the final cost is a Satoh of a cubic in the length of the input, which is a nice complexity, better than what we had so far. So yeah. And that's a way to get traces finally from all the ingredients that we presented today. So what do we have? As a further recap, we got a way to lift isogenies with whatever representation you like. We're implementing that in Sage. As a byproduct, all this abstract lifting theory has a computational counterpart that also gives explicitly the existence of the endomorphisms we're trying to lift. We got a trick to compute scaling factors, and we got an algorithm to compute traces, which we are also implementing in Sage with the hope to put it in the Sage library pretty soon. And yeah, that's it. The print will come at some point, so keep looking for that. And thanks. That was it. If you have any questions, happy to answer.
Thank you very much, Alessandro. As usual, you can just unmute or type your questions in the chat, whichever you're most comfortable with. Yeah, thanks. That was a great talk. Um, Maybe I can start. Um, so yeah, as you said, the complexity looks very very impressive. Can you apply this to point counting? Uh,
Um,
yeah.
so you mean can you apply the same algorithm to
So clearly
Frobenius?
not the smooth chain, but I mean, maybe I'm a bit unsure what I'm.
Yeah, the problem with point counting is that given the inseparability of Frobenius,
But
um,
create
there are
like
like theoretical obstacles to lifting.
okay.
A
Yeah,
cancel can't be applied, and
yeah, because like of course, as you're saying, you can't use Frobenius, but like if you use Frobenius plus something, or like yeah, I mean, you create HD representation of that. But I get no, wait, that doesn't make any sense because okay, yeah, compute. I mean, if you try to do, do
yeah,
Frobenius plus something, then you don't know the degree anymore. It would be the same as computing the trace of Frobenius. Like, never
yeah.
mind.
So I've thought about that, and indeed, it's kind of it seems kind of hard because of these obstacles. But
Yeah.
yeah, for sure, it's interesting. So we'll I'll give that a bit more thought. But yeah, thanks.
No, no, but yeah, no, it was a bad suggestion. Very cool. I mean.
We have a question in the room. Arun,
Yeah.
that's a question.
Yes,
Maybe.
I have a question. Can you put page 14 in your slides?
Can you hear Harun?
I can't hear that
Okay.
loud.
Now, do you hear me?
Okay, now that's better.
Can you put page 14 in your slides?
14, let's go. Here.
Yes, about the chain, it was confusing for me because if you start a Jacobian and if your endomorphism ring is not increasing, I think you cannot encounter with product, but you are saying we can. So can you explain how?
So the thing is like basically when we lift such a chain, what we do is like take the domain product of elliptic curves and lift these products arbitrarily. Like choose an arbitrary lift of E0, an arbitrary lift of E3. And then from that, we can always lift the steps in order to make them meaningful to isogeny steps in two dimensions. But if the lifts we chose at the beginning arbitrarily of E0 and E3 are not the correct one that lift this split chain, then we're basically ending up in a different kind of chain that that doesn't split in the end. Like we need the correct lift of the domain in order for this chain to be an actual lift that then splits as we expect. And for most of the other arbitrary lifts, this thing doesn't happen. Like splitting can be like the splitting of the final step of the isogeny can be represented as the vanishing of a certain polynomial expression. And with the wrong lifts, this expression doesn't vanish. I don't know how clear I am. I don't
Okay. I mean,
it,
Okay. I also had a question. I can ask one. I was wondering, does the performance of your algorithm depend on the representation? Like, is it better for HD or better for Vélu, or is it kind of the same? Like, like the general complexity is the same, but like in your implementation, do you see a difference or not really?
so the thing is, the complexity in the end ends up being like cost of arithmetic times the cost of the representation. So if the representation itself is more costly, then the trace computation will be more costly. So if we can compute an isogeny through a chain, then that's the way to go. And in the case where we use HD representations, they tend to be the most efficient thing. So they're the preferable algorithm. But yeah, so in general, the cost of that is directly proportional to the cost of the representation itself. So chains tend to be like a chain in one dimension tends to be just slightly faster because it grows as O of L instead of O of L squared. That is what we have in dimension 2. But apart from that, they're quite comparable.
Makes sense.
Hope it answers the question. thanks, Damien, for answering the question about lifting Frobenius and using point counting. Are there any questions? Any other questions?
Maybe I can ask, so when you have an HT representation, what does the complexity end up being?
For
Say it's like a, sorry.
yeah, what is it? Yeah. For an HT representation, the complexity ends up being O of E times 2 squared, like, yeah, O of E times K squared. So again, cubic, I'd say, in the logarithm of the degree. Right?
Okay, if there are no more questions, are there more questions? If there are no more questions, let's thank Alessandro again. Thank you, Alessandro. This was the last talk of this season. So thanks everyone very much for attending and for speaking, everyone who spoke. And then, as always, we'll be back with new killer talks next year.
And I guess since I'm the last one, I should also thank the lovely hosts for having this season and all the past ones and all the future ones.
Thank you.
And yeah, happy holidays to those who are taking holidays in Christmas. And yeah, see you next year.
See you soon.
So we can also hang out a bit